Okay, let's continue on with some of these examples. So just like last problem, we have this set of vectors v1, v2, and v3, and actually these are very similar to the vectors in the previous problem. However, now this last one is 1, 5, negative 10 instead of 1, 5, negative 8. And when we change that, we'll actually see that these end up being linearly independent. And how do we know that? Well, we can go through our row reduction that is written here. And we take R2, row 2 plus row 1, just like in the previous example, and that's going to make row 2 be 0, 3, 6. If we take row 3 minus 2 row 1s, we get 0, negative 5, negative 12. And if we keep going, I can multiply row 3 by negative 1 and row 2 by 1/3 to reduce to here. And then if I take row 3 minus 5 row 2, we get 1, 2, 1, 0, 1, 2, 0, 0, 2. This immediately tells us we are now in row echelon form, that we have 3 pivots. There are 3 vectors or 3 columns here, and if we have the same number of pivots as columns, that means there's just a unique solution to that linear system. And I'll remind you what that linear system was, right? It was this linear system right here, and it only has the unique solution because the number of pivots is equal to the number of vectors, and of course that means v1 through vk are linearly independent. So, we get that v1 through vk are linearly independent. So let's continue on with another set of examples here. All right, example 2. Let's let our vectors be the matrices E11, which is 1, 0, 0, 0, E12, which is 0, 1, 0, 0, E21, similarly defined, and E22, similarly defined. These are all vectors in the vector space, the set of 2 by 2 matrices with real number entries. And, well, pretty clearly, just like one of the previous problems, this is immediately going to tell us we are linearly independent, because if we write out our vectors here, right, this vector we can think of as the column vector 1, 0, 0, 0, so we write that out. 0, 0, 1, 0, 0, so we write that out, and so on. And we immediately see that we have 4 pivots and 4 vectors, so this set is linearly independent. Okay, let's have a not quite such a trivial thing to show now. With this set of vectors, and please ignore the scratching off, I am so sorry about that. I am redoing this part of the video because I dropped a negative essentially. We have these vectors now, A1, A2, A3, and A4. Again, these are vectors in that same space as the previous problem, right? The set of 2 by 2 matrices on real number entries. And so we can go through and we can write this out. A1 is the vector 1, 1, 1, 1, so we write that out. A2 is 1, negative 1, 0, 1, right? 1, negative 1, 0, 1. And then so on. So we write out A3 and A4, and we get that matrix there. And from there, we can start row reducing. Well, I just took, for this first step, I actually just subtracted row 1 from each of the other rows to figure that out. And so that cancels out row 4 entirely, which tells us already at that point that we are linearly dependent, as in these vectors are all linearly dependent, right? The set of vectors is linearly dependent. Let's keep going. I did some just changing of rows around here and then multiplying by -1 just to try to simplify things. You don't actually have to do any of that, but I think it helps on the calculations here at the end. So I swapped row 2 and 3 for here and then multiplied by -1. And then finally, my last step there was to take row 3 and subtract off 2 row 2s, and we get this system here. Or we get it reduced down to that. Now what does this tell us? Well, this tells us our free variable is C4. right? We have a pivot in column C3, we have a pivot in column C2, and we have a pivot in column C1, so those will be our basic or leading variables. We have no pivot in this column, so C4 is our free variable, and I'm just going to call that T. Now, what do we get here? In this third row, we get 2C3 minus 2C4, which I'm calling 2, is equal to 0. This tells us 2C3 is equal to 2T, or in other words, C3 is equal to T as well. And then we can keep going. C2, 1C2, plus 1C4, which is T, which I'm calling T, is equal to 0, so C2 is equal to negative T. All right. And then finally we get C1 plus C2 plus C3 plus C4, which I called T, is equal to 0. If I plug in what C2 and C3 are, we get C1 minus T plus T is equal to negative T. Those cancel. The negative T is because I just subtracted over. So C1 is negative T there. Now, what does this tell us? This tells us we get T times negative 1. C1 was negative T, right? So negative 1T is the first row. C2 was negative T, so it's negative 1. C3 was positive T, so it's positive 1. C4 was positive 1. So this right here is a non-trivial solution for any T there. That is a non-trivial solution to our linear combination of A1, A2, A3, and A4 equal to 0. So in particular, I can take T equal to 1. If T equals 1, then this gives us that negative 1 as our C1 times the vector A1, which was 1, 1, 1, 1, minus 1 times A2, which is 1, negative 1, 0, 1, plus 1 A3, which was 1, negative 1, 1, 1, plus 1 A4 is 1, 1, 0, 1, should all equal the 0 vector. Let's check. Let's see. Negative 1 minus 1 plus 1 plus 1 is 0. Good there. Negative 1 plus 1 is 0. Plus a negative 1 plus a positive 1 is 0. Fantastic. Negative 1 minus 0 plus 1, so that's 0. Plus 0 is 0. Great. And then negative 1 minus 1 is negative 2. Plus 1 is 0. So we were correct. And the final step was to write out the one of these as a linear combination of the others. So what if I take this vector and I move it over to the right-hand side? So it'll be a positive 1 times A1. And that tells us that negative 1 A2 plus 1 A3 plus 1 A4 is equal to positive 1 A1. And so I've written out one of these vectors in terms of the other three. All right, we just got two more examples to do. Let's do those real quick. And these are going to be on polynomials for our vectors. All right, let's determine if 1x, x squared, and x cubed are independent. So reminder that if we have the polynomial 1, we can write that as 0x cubed plus 0x squared plus 0x plus 1 is that vector, and we'll call that v1, I guess. Well, let's write that as 1, 0, 0, 0. So the coefficient on the constant term, then the coefficient on the linear term, coefficient on the squared, coefficient on the cubic term. All right, if we do that, let's keep going. Well, x, then the vector x is going to be 0, 1, 0, 0. the vector x squared is going to be 0, 0, 1, 0, and x cubed is 0, 0, 0, 1. And as we see here, we have 4 pivots, 4 vectors, so these are absolutely linearly independent. Okay, now let's do a similar idea with some not quite so trivially easy to show set of linearly independent vectors. Let's go ahead and write these out. All right, I have the vector 1 plus x, so that is 1 constant 1 term plus 1 x term plus 0 x squared plus 0 x cubed, and I am going out to x cubed. As I see, I have 1, 2, 3, 4 vectors here, and also my highest power is x cubed. All right, so vector 2 is going to be 0, 1, 1, 0. Oh, nope, that's not a comma there. 0, 1, 1, 1. Sorry about that. I can't read. Oh, and in fact, we just have 3 vectors here. That's why I was confused. I said 4 vectors just a moment ago. I can't read. So we have 1, 1, 0, 0, 0, 1, 1, 1, and 1, negative 1. Oh, and there we go. I am honestly having trouble reading this. All right. Don't know why. So, we get this. Actually, we already know, and you might ask yourself why, pause the video and say why, but we already know that these are not linearly independent. Okay, so think about that just one moment. All right, now why is that? Why are these not linearly independent? Well, we only have 3 vectors here. So let's see if... Oh, never mind. I'm sorry. I'm thinking the wrong thing. I'm not restarting this video. They could totally still be linearly independent. We have 3 vectors. We don't have 4 vectors. I keep thinking 4 vectors for some reason here. So we have only 3 vectors. So we can absolutely, if we just have 3 pivots, we're all good. They could still be linearly independent. All right. So sorry about that. Absolutely, these can be linearly independent. We just have 3 vectors here. And so if this has 3 pivots, then we're good to go. So let's keep going. Let's go ahead and try to simplify this. I'm going to take row 2 and subtract off 1 row 1 to help row reduce here. And we get 1, 0, 1, 0, 1, 1 minus 0, and then 0 minus 1 is negative 1. All right, I'm not adjusting this row at all. All right. And now, what do we get? Well, 1, negative 1, 1, negative 1. Here, okay. Oh, and 1, negative 1. Actually, now we are going to see that we are dependent and not linearly independent. And this is how we know right here. Okay. So we couldn't immediately tell, but it turns out it was true. All right. So if I'm going to take row 3 and subtract off row 2. And I'm going to take row 4 and subtract off row 2. And if we do that, we get 1, 0, 1, 0, 1, negative 1, 0, 0, 0, 0, 0, 0. Okay. And so our free variable is going to be C3. And our other variables, well, let's take C3 equal to T. Then C2 minus T is equal to 0, so C2 is equal to positive T, and C1 plus T is equal to 0, so C1 is equal to negative T. So if we do that, we get that C1 is t times -1, C2 was t times +1, and C3 is +1t. Okay, so this right here is a set of non-trivial solutions to our system. All right, now, what does all of that mean? Well, in particular, if t is equal to 1, then we get 1 times the first vector, which is 1 plus x. Sorry, -1. -1 times that first vector, 1 plus x, plus 1 times vector 2, which is x plus x squared plus x cubed, plus 1 times vector 3, which was 1 minus x squared minus x cubed, is equal to our 0 vector. Let's confirm that, right? So we get -1 and a +1, so our constant terms are 0. We get a negative x here and a positive x here, so our linear term is 0. We get a positive x squared and a negative x squared here, so 0. And we get a positive x cubed and a negative x cubed, so 0. So in fact, this worked absolutely correctly. And we can write down 1 in terms of the other 2 by just adding this over to the other side. So we're going to get x plus x squared plus x cubed, one of those plus 1 of this vector is equal to 1 of our first polynomial, 1 plus x. All right, and so we've been able to write out one vector in terms of the other 2, and absolutely this is a set of linearly dependent vectors. Okay, thank you, and that concludes our examples on linear independence.